All right, everybody. We're in just a little bit early. I would love to know. Here's the poll. Oops. I think I accidentally. Yep, I did. All right, so we'll try the poll again. I'm going to archive that one. Let's do a new one. All right, here we go. All right, here we go. Now let's try this again. Here we go. Poll is open. Let's share the poll. So I'm going to show it. If you were a Star Wars Mandalorian character, who would you be? That is the question. In the chat, I'm going to put the link to our, I will put a chat. Thank you for letting us know, Brianna. That's awesome. So in the chat, I'm going to put the link to Pear Deck. We would love for you to get on to Pear Deck because we are definitely going to use Pear Deck tonight. Tonight is all about free response tips and tricks. Tonight's really about experiment design and analysis. So that one's super, super important. This is a 12-point question, so it's worth a ton of points. And we want to make sure you do well on this. So hopefully this will work out pretty well and kind of show you what it looks like. And I think that's the good thing. As you notice in the chat, you also see that tonight there will not be any forum tonight. Brianna has some other things going on, so she's going to go do those things, and it will be rescheduled for later in the week. So just letting you know that right off the bat. So we're going to hopefully see that again here soon. And that should be a great thing. So we'll do that. But as you come in, there is a forum. There is a forum. There is a poll we would love for you to answer. And that poll is on the screen there. You'll see it. We just want to know, if you were a Star Wars Mandalorian character, who would you be? And if those are your only choices. So you could be Cara Dune, you could be Mando, you could be Yoda, and I know he's not really a Mandalorian character, but he is a Star Wars character, so I added that. And then Grogu. So that gives you plenty of options. That's all I could put into the poll, so that'll have to do. So hopefully that'll work out pretty well. And we have 1 minute to go, and then we're going to get started here. And we'll keep putting that link in the chat so that you know where to go. I think some of you are already on it because you're able to do it without the chat, which is awesome. And we'll give it just a couple more seconds here. And hopefully that will be super helpful. Oops. I have some interesting facts for you tonight, too. I want to show you about the AP test because I think you'll be pretty pleased with this. All right, I have 6 o'clock, so let's check out the poll, see what everybody wants to be. Oh, I love it. So here's our results. Our results are Cara Dune, 1 vote, Mando got zip, and Grogu didn't get any. So the 2 main characters did anything, and the person who's not really in it, but just in Star Wars itself, is Yoda, and Yoda gets the big kick. So way to go, Yoda. All right. Let's go ahead and get rolling on the Pear Deck. We will also put in the Pear Deck. In the chat, we'll put the Pear Deck link, and hopefully that is super helpful for anybody that gets in that can't see the code. All right, let's start this up and see what we know. So we're going to talk about free response tips and tricks, and this is all about experimental design and analysis. Please, heads up, do know that we are recording this. So it might appear on our website, YouTube, or other public channels. If you do ask a question, your name might appear on the screen. So make sure that if you have your name somewhere in this, if you want to change it, you sure can. But that shouldn't be a huge deal. Think Fiveable is where we're at. Get it? That's where we're at. Anyway, you'll notice that we do tweet. Love to have you tweet about what you experience. Hopefully it's awesome tonight. You could do Instagram. You could do Discord. You could do TikTok. You could do YouTube. You name it, and you could do it. And you can kind of let the world know that we're out here to help students. And that's the most important part. All right, so let's talk a little bit about what's coming up. We do know that next week is free response tips and tricks. This one is on QQT and paragraph length response. Tonight is only on experimental design because it's a pretty big one, and it's one that you can do really, really well on. The Cram finale will be on 5/4, so May the 4th. It starts at 5 p.m. and it is 4 straight hours of fun, physics, and getting ready for the AP exam. In this stream, we're going to talk about what the question is, the physics principle, what do you need to graph in order to do well on this, the experimental procedure. We're going to talk about the d-squared method. It's a really nice little method. We'll talk about data analysis and the physics equation that you need to try to create for each one of these. One thing I do want to show you, and this is pretty important, I like to use the rule of sevenths. And the rule of sevenths goes like this. You want to think about the AP test not like a grade in your class. So if you take a test and you get a 43%, most of the time you'd say that that's an F. A 57% would probably still be an F, and a 71% would be a very low C. Some schools it might be a D. It just kind of depends. When you take the AP test, that 3 out of 7 is actually very good. So that 43%, really don't pay attention to the percentages. Pay attention to the fact that if you can get a 3 points on everything out of 7 points, or 5 points out of 12, or you can get 43% of the multiple choice correct, you are on task to get a 3 on the exam. And remember, that's a qualifying score. A 4 out of 7 is a 57% or somewhere around there. And these numbers, they do change from year to year, kind of based on how the questions roll and that type of thing. And then notice you need about a 71% to earn the score of 5. So if you get an 80%, you get a 5. If you get a 99, you get a 5. So those are the things that you kind of want to think about. Let's go ahead and get into what we mean by experimental design. So here we go. Here is the question that we're going to try to answer tonight. These little toys are really cool because you take the toy, you press it down, it stays there for a second because it has a suction cup on it, and then it pops up. And when it pops up pretty high. So my question is, how could you find the spring constant value for a jumping toy using the conservation of energy? So most of the time, AP questions deal with some sort of conservation. Sometimes it's conservation of energy. Sometimes it's conservation of momentum. If it's not one of those, it's probably something you're going to have to use Newton's second law to do. So always remember those three, because when we talk next week, we're going to talk a lot about those three and how when you go through and explain something, if you use Newton's second law, if you use conservation of energy or conservation of momentum, you're on the right track. Not that you can't do it other ways, but those are the three biggies that we've seen as we go through. Hey, remember, if you just came in and you want to join the Pear Deck, we'll put that link into the chat one more time. For this one, we want to provide enough detail so that another student could replicate the experiment so that they could do the same thing. And we want to include any steps that we use to reduce experimental uncertainty. So we don't want any outliers. If we do, we want to be able to account for them. So as needed, we're going to use the symbols defined in a table and or include a simple diagram of the setup. So every single year on the AP Physics 1 exam, you have one of these questions, and every year it is 12 points. Now, I will tell you, if you are taking the digital exam, you will not have one of these. Instead, on the digital exam, you will have one paragraph length response and one QQT. Hence why next week we're going to do the QQT and the paragraph length response. But if you're taking the paper pencil test either on May the 5th or on May the 24th, you can expect one of these. And we're going to show you how to get the maximum number of points possible on this one. So here we go. Since the question states conservation of energy, we need some sort of an equation, okay? There's two ways to do this. We can either think about going from potential energy of a spring to kinetic energy, or from potential energy of a spring to potential energy of gravity. I want you to set these two equations equal to each other. So for example, that's US spring energy, set that equal to kinetic energy, and then go ahead and put what each one of these stands for. So you'll need to give me what is US. So what is the equation for US, and set that equal to the equation for translational or kinetic energy. If you want to do this using spring energy to potential energy due to gravity, you can do that. So you'll start with US, whatever US is, and make that equal to whatever UG is. So go ahead and do that. I see some people doing it already. That looks awesome. And then I want you to solve for K. I want you to solve for K. That's the first thing that we're going to do. This will help us as we go through and do the setup. And when we think about what we're going to graph, this is a really important thing to do. They usually ask you, or they say, use conservation of energy, but that just means that there might be a lot of different ways to go through and do this. So go ahead and take your time. I'm seeing a lot of great answers so far. Very nice. I like it. Excellent job so far. And then go ahead and solve those for K. You want to solve these for K, the spring constant, not kinetic energy, but go ahead and solve your two equations that you have. Go ahead and get those down to K on one side and everything else on the other. Lily, you're doing great. Grace, that's fantastic. Good job. Kritika, very nice. Josh, excellent. You folks are on this. Good job, Giesel. Way to go, Brianna. Excellent. So we're just trying to solve these for K. Looking really good. I like what you're doing here, guys. Thank you for doing this. Excellent. Beautiful job. Job, Lily. Okay, Grace, nice. Good job, Kritika. Good. Good, good, good. Excellent. All right, so we've got a lot of great answers. We can kind of take a look at what you did. Here's one. We've got K. And remember, this K is for the spring constant, not for kinetic energy. We've already put that in over here. And they have mv squared over x squared. Here we've got 2mgh over x squared, so that's excellent. Same thing here. This one I think is missing the 2, so watch out. There is a 2 here because remember on the left it's 1/2 kx squared. Do remember that all your equations are on your equation sheet, so you're able to go in and take a look at those. So this looks great. Nice job, guys. All right, so let's check out what the real answer is, and this is the actual answer. So we did 1/2 kx squared is equal to 1/2 mv squared. The halves cross off, and then we're just left with mv squared over x squared. Remember, x is the compression distance, m is mass in kilograms, and v is our speed or velocity squared. On the other side, notice we can't cross off the half, so we do have to multiply both sides by 2. That gives us 2 mass, gravity, and then I put in delta y here. That should help a little bit, and then we've got x squared on the bottom. So fantastic job. Now that we've done that, we can go through and we can figure out what needs to be plotted to obtain a slope that equals the spring constant. So here's what I'd like for you to do. I want you on the y and the x-axis for each one of the two graphs to put down what is it I need on the y-axis and what do I need on the x-axis in order to get a straight line from the equation above it. This is not a trick question, and it shouldn't be very tricky. If you want to use the typing tool, please feel free to do that. It makes it a lot easier, I think, to go in and put down what you want on the different axes. So go ahead and do that, and then we're going to check some of your answers and just see kind of what you get. Remember, we are trying to get a slope that actually equals the spring constant. So we're trying to get a slope that equals the spring constant. And you can do both or either one, doesn't matter to me. But I'd love to see what you would put on each axis in order to get a slope that would give us the spring constant. Looking good. You guys are doing great. And you're going to kind of see when you get done why we did the equation first. So why we did the last slide, then you're going to see why we do this slide, and then you're going to see why we did the whole thing. Okay, you guys are doing great. I'm starting to see some answers here. Excellent job. Very good. So we're looking, what are we going to put on the y-axis and what are we going to put on the x-axis in order to get a straight line right off the bat? You guys are doing fantastic. Excellent job, ladies and gentlemen. I like it. All right, looks like most people have an answer. So let me kind of show you what some people did. So I see a lot of great answers here. We've got mv squared here. We have x squared here. We have 2mg delta y and x squared. This one they did 1 over x squared and mv squared, 1 over x squared and mgy. Good. Velocity, displacement, gravitational potential energy, and displacement. So we see that. Here we've got mv squared, and then they put in the units. Good. And then same thing here, and they put everything in. And then somebody said, no, maybe I don't want to do that. And that's absolutely fine. So here's our answer. So it's really important when you draw a graph, when you put your labels on, you also need your units. So kudos to that person who did your units. And here's kind of the really cool thing about having an equation. So you'll notice we solved both of these for k. If you noticed up top, remember m is slope. And our equation for slope is the difference in the y's divided by the difference in our x values. So it's just delta y over delta x. Well, you'll notice this is m, so k is our slope. y2 minus y1, that would be the value we get if we take the mass times the velocity squared. And then our x value would be x squared. So I literally just took, here's my y, I put it right here. And then I had to remember, well, what are my units? Mass is kilograms. Velocity is meter per second, but I have to square and be really careful that you square both. Velocity, you square both the meters and the seconds. Since you're squaring velocity, you have to square both. Then on the bottom, I have x squared, so that's the compression or the stretch squared, and that's in meters squared. So don't forget your units. Same thing on this side, 2 mg delta y, so that's a kilogram meter per second squared times a meter. And then on your x-axis, you have x squared, which is in a meter squared. If you go through and you put this unit on top of this one, that would be the unit for your slope. And you'll notice it's a kilogram per second squared. And everybody says, yeah, but you said spring constant. That's in newtons per meter. Guess what? Here's a Newton. Here is a meter, and the other meter crosses off. So now you're left with the meters getting crossed off, and you're left with the kilogram per second squared. And so that's also a unit for the spring constant. All right, excellent. Way to think. Now you kind of know a little bit about why we are thinking about what we would graph and where that takes us. So in our experimental procedure, some of the things that we do, I like to do something called D square. So I'm going to tell you what each part is, and then I'm going to have you actually try this part. So remember, our question in the lab question was to do the following. So I'm going to back up here. How could you find the spring constant value for a jumping toy using conservation of energy? So we kind of know what the equation is. We need something. We either need to have the speed and the compression of the spring, or we need to know how high it goes in the compression of the spring. So either pair would be fine. Do you really need the mass? Well, if you don't use the mass initially, you'll have to multiply your slope by mass. So if you go ahead and say, well, I need mass, and I'm going to measure mass, you could do that too. So I know I have to measure the spring constant. I have to measure X, which is the compression. And I also need to measure speed here, or I'm going to measure compression, and then I'm also going to measure the height that this thing goes. Most other things are constant. And if they're constant, we can go back in and add them later. So what would you do, or what would the picture look like for your setup? Now, when I say that, I'm going to tell you, you're going to want to go in and draw. But when you draw your setup, we're going to make it a stick figure setup. And a stick figure setup means make everything a stick figure. So if you're going to use a balance, I want you to use a stick figure for a balance. So draw a box and then just write balance, either above it, inside it, below it, to the left or to the right. Doesn't matter, as long as it's really close and we can tell that that's a balance. If you need a meter stick, literally draw a meter stick, put some marks on it, but you don't have to put 100 marks on it. It doesn't even have to be spaced out well, but you do need to label it meter stick. You got to put the toy in there. So you probably want to write toy and draw the toy. And then probably something that we want to set that toy on. So maybe you just have a table, but you don't need to label the table. You could do this on the floor, I guess, if you want to. So you want to draw the toy. If you want to measure mass, you'll have to draw a box. And then on top of the box or in the box or somewhere on the box, you'll want to write balance or scale. You can do anything like that. But those are the things that you'll want to draw. So to save you from having to draw all of that and to save a little bit of time, here's what I did. So this would be 100% acceptable. You really just need the bare necessities. All I drew here was I drew a table, but I didn't label it because I just want that table to be sitting there. I did draw the spring toy, and I put a nice happy face on it. I drew a ruler/meter stick, and I put it up next to the toy. And then I have a balance, and I just drew a box with a little circle in it, tried to put some numbers on it. That's if I do the gravitational potential energy part. If I do the one where I want to find out how fast it leaps off the table, I need a motion detector because I want to find the speed. But you need to make sure that you place it in an appropriate spot. I put it here because it's going to see it moving towards it. If I put it over here, it would see it go by, but they don't measure very well in that direction. So if you're going one way and this is measuring to the left, it probably won't find the actual speed. We really need to be going towards it for it to find that speed. So there's our picture. The next steps, there are 3. So remember, we're doing D. D stands for diagram. And then we're going to do SQ, U, and A. So you'll notice here, these three, well, they're not really three letters, but they are SQU. We'll call that one thing. And A, we're going to do all three of those steps together. So S stands for setup. This is where we briefly explain anything about the experimental setup that the diagram doesn't clearly convey. So one of the things that we can think about here is, how are you going to get this spring toy to jump up? How are you going to do that? So that's one thing we have to think about. We also need to think about, what things do I need to measure directly? And then if I measure anything, what apparatus do I use? So here I went ahead and I said, ooh, I want to measure height, so I'm going to put in a meter stick. Or I want to measure velocity, so I'm going to use a motion detector. Or I want to measure mass, I need a balance. So whatever it is that you're going to measure, whatever quantity, if you don't have an apparatus, it makes it really hard to go through and talk about what's going to happen. So here's a good example. Use a meter stick to measure the height of the top of the ramp. Use a stopwatch to measure the time it takes for the block to go down from the top of the ramp to the bottom. So that's an example using something on an inclined plane. Because we have our two equations, I'm going to have you do the setup, quantities, and apparatus. And really, you can just do quantities and apparatus here. We'll talk more about the setup in a second. But I want to know, what two things are you going to measure in each one of these? And what are you going to measure them with? In here, if you want to, on an experimental design, you can number things. You can put bullet points. You do not have to write in a paragraph, and you don't have to use complete sentences. So I'd love you to use the equations here, tell what two things you're going to measure and what you're going to use to measure those. If you want to measure three things, that is absolutely fine. So if you want to measure three things, go ahead and put in what three things you're going to measure. Because we did say that if we plot mass times velocity squared divided by the position squared, that would give us K right off the bat. So if you want to measure mass, that would be helpful probably. You would not have to, though, in this part. So I'm seeing a lot of you do this, which is fantastic. And remember, there is a typing tool. So if you want to type your answers, you sure can. So remember, we started by saying, well, we want to find the K. And remember, K is the spring constant for our spring. And there's two ways to do it. We can either say the spring energy at the bottom will be equal to the kinetic energy right when the spring takes off. Or we can say the spring energy, which was 1/2 kx squared, is equal to the potential energy when that toy gets to the very top. So we solve for K. Anything is on the top, we keep that together, and we put that on our y-axis. And anything on the bottom, we put on our x-axis. So same thing on this side. Now we have to figure out, what is it we absolutely have to measure? What are the things that are going to change? And so if I change the spring stretch, I could do that. That'll change the speed, but that won't change the mass. So really, I don't need to include mass in my procedure for this part. Same thing over here. If I change the stretch, it'll change how high it goes, but it won't change the mass or gravity. And then 2 is just a constant. So you guys are doing pretty well here. I like it. Looks really good. Seeing some good answers here. Good. Yeah. No. Critique of that looks good. And remember, we're not worried about grammar. We're not really worried about spelling and those type of things. You just do the best you can. We're not going to take off for grammar or spelling. We're just looking for, do you understand kind of how to do an experiment? And when you go to college, we'll have the college professors in English worry about your spelling and grammar and things. But for this test, we're not too worried. So I love what this first person did. They said the distance the spring is stretched or compressed will be measured by the meter stick. So awesome. The speed of the toy will be measured by a motion detector, and the mass will be measured by a balance, and it will be constant. So that's awesome. So you only know you have to do this once. Got some other things, same type of thing as we go through, telling kind of what we're measuring and what we're using to measure it with. So I love that. This person did a great job on this side, figuring out the mass and using a scale, the displacement of the object using a meter stick, and the displacement of the spring. So excellent job. So very, very, very nice, guys. Cool. All right, ladies and gentlemen, here we go. This is what I did. I said measure the mass of the toy with the balance, compress the toy on the table, and measure the compression with a meter stick, and then let go of the toy. And when it rises, record the velocity of the toy using the motion detector. I wrote in complete sentences, but you do not need to. Same thing here is measuring the mass of the toy, compress the toy, measure the compression, and then we're going to measure how high it goes. And I even included here in the end, to be more precise, use a cell phone slow motion camera to better see the height, because I can scroll back and forth on it. So notice that our setup includes some of those things about compressing the toy. But I always talk about what am I going to measure and what am I going to use to measure it. That's really what we're looking for. So when we score these, we are definitely looking for what are those things that you are measuring and how are you going to measure it. So excellent job. There are two more points that we have to go through on this lab. One of them is, what are you going to repeat and how are you going to change it? So what is your repeated independent variable? That's the thing that I change. So remember, independent variable has an I at the very beginning. And because it has that I in the beginning, that's what I change. And then my y-axis will change, and it's the dependent variable. It depends on what I chose. So here we're going to just state how the trials are repeated, including what quantity will change and how it will change. So I might say for 5 trials, increase the height of the top of the ramp on each trial, but keep the length of the ramp the same. So that's if I'm measuring something using an inclined plane. Error reduction. Lots of people do this a lot of different ways, but for you to get credit, the easiest and the best thing to do is say, do each run 3 tries and average. Or do 5 trials and, do 3 runs for each trial and average those runs for each trial. Let's go ahead and try that on this one. So remember, your X variable is typically what you change. So on both of these, we've made it really super easy to think about what to change. It's on the X-axis already. So what I'd love for you to do is do 2 things. Just say, what are you going to change? How much are you going to change it by? And then after that, how are you going to reduce error? So what are you going to change? What are you going to change it by? So what value would you want to change it by? And then what are you going to do to reduce error? So take your time, go ahead and go through that. All are doing a great job. I had trouble getting the closed captioning to come up again today. You all are doing fantastic. I love it. Good job. Excellent job. And remember, when we reduce error, we always want to say we're going to do several trials and average those trials together. That's really all you need. That's really all you need in order to do this. Yeah, very good. Excellent. All right, so let's just take a look at one of these answers. It says perform multiple trials, changing the displacement value each time. So this is great. I think to make it even better, we could say perform multiple trials, starting with a compression or a displacement of the spring of 2 millimeters, and then increase that value by 2 millimeters each time until you have 8 data points or something like that. But I love what they did for reduce error. To reduce error, record the velocity at the same distance multiple times and average to get a more precise answer. That is how you reduce error. So that's perfect. When we say decrease mass, so now we're actually changing something on the top. You could do that. And when you do that, that will definitely affect the speed. But then we need to say that keeping that compression the same. Sorry, excuse me. Here, we want to say increase this or decrease the bottom, and that will change what's on top. So remember, we're always looking at changing the X thing. So whatever's on the bottom, and it just happens that this is represented with an X, and then repeating each trial 4 times and find the average. So that is awesome. Good job. All right, so let's go ahead. See what I did. I said repeat the steps, but increase the compression each time until 7 data points are obtained. For each run, do 3 trials and average the data. So I did exactly the same thing on both. So you'll notice it doesn't matter whether I am using speed or height. I'm using the same repeated variable, and I'm doing the same thing for reducing error. So hopefully that's helpful. Cool. Now let's talk about data analysis, because this is another part where students have a little bit of trouble. We always want to include our measured variables first. So whether that's mass or position or compression or speed, anything I measure, I always want that in my data table first. Then if I have more things, for example, I might calculate something like, I might calculate velocity, acceleration, kinetic energy, potential energy. For each one of those, make sure you explain really how you calculated that column. So if I found initial kinetic energy, I'm going to do 1/2 mv squared. If I did final, it might be 1/2 m1 v1 plus 1/2 m2 v2 and all those other things. You really don't need to put any numbers in your table unless data is given or you're specifically asked to do that. So whatever numbers you put in, make sure they don't violate any of the basic physics principles. If I can't measure anything directly, make sure you really do include the equation. So when you look at this slide, I'd be able to measure both mass and velocity very quickly and easily using a tool, but kinetic energy and momentum, I would not be able to do that. I would have to put in those equations. So that's kind of pretty important. When you do a graph, the first thing you want to do is determine and then explain what should be plotted. So we've already done that. We said that if we're doing this lab, we would put compression on the x-axis and then either mv squared on the y-axis or mgh or mg delta y on the y-axis. Then we can sketch a plot of what it looks like. From that shape, we could go through and talk about the slope and do some other things. This also shows you the different names of the different curves. And so you might have to do something with the shape, or you might find the area under the curve. So all kinds of different things that you can do with the graphs. I want to focus just really on this one thing right here. And this is writing a physics equation. So sometimes you're going to be asked how to show, they'll say, what is the linear relationship between the variables, or how do they relate? The easiest way to do that is to write what I call a physics equation. And a physics equation is just like an equation for a line. So remember, the equation for a line is y is equal to mx plus b. So what is on our y-axis? You'll notice velocity is on our y-axis. So I went ahead and put that in the spot where I normally would have the letter y. Then my slope goes next, because remember, it's y is equal to mx plus b. So here's my slope. It's 0.101. So I went ahead and just put in 0.10. I just rounded it to the nearest hundredth. And then I put in my units. My units are whatever my units are on the y divided by whatever the units are on the x. So that'd be a meter per second, or a meter per second squared. Now I have y is equal to m times, and now I have to put on whatever is my label on my x-axis. That's time. Plus b. And for this one, my b value is super small, so I'm just going to put 0, or I could just leave it off. A lot of times, you just need these three things. And what's cool about this is one of those physics equations you use all the time. It's v is equal to acceleration times time. So the change in velocity is equal to the acceleration times the change in time, and that's it. So that's how we go through and try to represent what our graphs tell us in an equation. And then we can do other things with it. Let's go ahead and we're going to have you go through, and we're just going to do a couple of these. I want to know, and you don't have to draw a diagram, but I do want you to explain what you would set up, the quantities you would measure, and then what apparatus would you use to measure. So we've got Bendy Straw and Annabelle, and they're trying to determine the acceleration of a toy car. Assuming they have all the equipment you would commonly use in a physics lab, explain a procedure in which they might find the acceleration of the toy car. So I'm going to say, on your mark, get set, go. If you want to skip the diagram, that's absolutely fine. But I do want you to give me the setup, quantities, and apparatus. So think about, what is it we're trying to find? Remember, we're trying to find acceleration. Is there an equation for acceleration that you know? If you know that equation, make it so that your acceleration is your slope. Then what would be on the y and what would be on the x-axis? At that point, tell me what you're going to measure and what you're going to use to measure it. So we're looking for the acceleration of a car. All right, I'll give you a little bit of time to try to figure that out. I do think, let's do this. If somebody can give me the equation for acceleration, just the most basic equation for acceleration, that might help everybody out. So if somebody wants to type that, then we'll take a look at it, and then I think that will help you figure out what your quantities and apparatus are that you need to measure. So if anybody knows the equation for just acceleration, go ahead and write that. All right, here we go. We've got somebody doing it. So we want to know, what is the equation for acceleration? And there are three, but we just want the most basic one. Yeah, perfect. So I want to show you what this person put. They put acceleration as the final velocity minus the original velocity divided by the change in time. Now, here's the other thing. If I go to Google and type in AP Physics 1 equation sheet, and then click on the first link, and then pull the equations up, you will see that equation, believe it or not. It's this very first equation on the left side. Let's make it even bigger so we can see it. So here's our equation, but we want to solve this equation for A. And if we solve it for A, we'll get exactly what this person did. So now I know if I want my slope to be A, I need to measure two things. I need to measure the change in velocity, and I need to measure the change in time. So what would you use to measure the velocity change? And what would you use to measure the change in time? So now I think everybody should be able to go in, tell me what quantities do I need to measure, and what apparatus am I going to use to measure them? Now I'm starting to see some good answers here. So I'm seeing some great equations you guys have put on. Oh, very good. And I want to know, what am I going to measure? And what am I going to use to measure that? Oh, yes, absolutely. Let's get the code for the Pear Deck back in there. Sorry about that. I meant to put it in several times, and I just have not done that. So it is now in there. Sorry. You're so welcome. All right, I'm starting to see some really good things. Oh, excellent. I like it. Good. Excellent. So we've got some great answers here. Let's take a look at some of these. This person is going to use a motion sensor for that velocity so we can see the velocities. And then they're also going to use a stopwatch to measure the time. So good job. Here's a little bit different way to do it, but this would also work. We want to find the displacement. So we're going to use a meter stick. And we find that displacement, and we also need the time. So we're going to use a stopwatch. Now remember that displacement, because it's speeding up, is going to change, but we would be able to make a graph and then linearize it and then find the acceleration from that. So that is another fine way of doing it, as long as you analyze your data correctly. So here's another one where they're using a ruler meter stick in order to find the velocity. So they're typing that in, very good, to find the displacement, and then they'll find the velocity. Excellent job, good. Here's another person. They drew everything. I like the slow motion camera. The stopwatch will measure the time the car takes. And then the slow motion camera will be used to find the velocity. And you had position in here, which I absolutely love, because you do need to know those positions. If you know those positions, you can actually plot the positions and the times, and then you'll get a curve, and we can change that so that we can get the acceleration from that curve. So excellent. You would use a stopwatch to measure the time and a meter stick to find the displacement, and then stopwatch for time so you can do the meter time thing to get velocity. Excellent. Nope, that would work. All right, good job, guys. Fantastic. So now that we've done that, what is it that we're going to repeat? So what is our repeated variable? What is it that we're going to repeat and change? So what could we change, or do we need to change anything here in order to figure out what the acceleration of the toy car is? So that's kind of that question that's a little bit harder to figure out. Does anybody have any ideas on what you might change? So one of the things that you can think about is this. If I record the time at each one, very good. So here's a great answer right here. Distance. I can change how far the car goes each time and the time. So that's perfect. So if we do that, we're going to get a curve. So now here's the next part we're going to do. We already know what to do for E. Remember, E is error reduction. We're just going to average our values for 3 trials for each one. Okay. So now in our data table, let's think about what is it that we measured. So we know that one of those things we measured was distance. And the other thing that we measured is time, and that we changed the distance. As we change that distance, that will change the time. You could also put change in velocity and change in time, and that would also work. On the graph, let's do this. Go ahead, and I want you to put, let's do time on the bottom, and let's do position or distance. Yeah, let's do distance here. So we're going to do distance here. We're going to do time on the bottom. If you have something accelerating, I want you to show me what the curve would look like. This is not going to be a straight line. It's actually going to be a curve. So grab that drawing tool and show me the curve of what it looks like when something accelerates. This is a great little thing to do. Good job, Josh. That would be correct. Excellent. Excellent. Good job, Giesel. Good. Grace, perfect. And then Grace, on your x-axis, go ahead and take off the last 2 things because we're not there yet, but we're about to go there. So if you take those last 2 symbols off, then it would be correct. Excellent. Okay. So for this one, we want to be really careful. We want just distance and time. And you'll notice that this is smiling. And if it's smiling, that means that it has a positive acceleration. So excellent job. I love the smiley face there. So it looks like a lot of you did that. Okay. Now here's what I want you to do next. I want you to change what you have on the x-axis so that it would make it a straight line. So if I want a curve, like the curve that we see here, to be linearized, what would I have to do? So remember, this would be a quadratic relationship, which means that y is equal to x squared. So I need to do something to the time, and I'll tell you what, Grace, you had it originally. So Grace, go ahead and put in what you had right after the time. So put that back in and then erase your curve and put in a straight line. And we'll see if anybody else gets it. If you did velocity time, you can leave it a straight line. If you did velocity time, you can just make a straight line. But if you did position and time, you can still find the acceleration, but you have to do something to one of your axes. And Grace did it. So Grace, go ahead and put in a straight line. Perfect. So here's what Grace did. She has distance and time squared, and she gets a straight line. Hey, Grace, do me a favor. Put a 2 on top of the line. Put a 2 on top of the line. So there is what Grace did, but I want to show you some of these others. If you have velocity and time, you can just put a straight line because that velocity versus time is the acceleration. So distance and time squared, that would be correct. Very good job. Velocity and time would be a straight line. So very nice. Let's see, who is this person that did this one? And we're going to have them do, okay, so Pratush, if you could put 4 right here on your slope, that would be awesome. If you could put a number 4 right here, that will help us out. So if you don't mind, Pratyush, putting a 4 right on your line here, that would be great. Perfect. So notice that the acceleration of this toy car is 4 meters per second, or 4 meters per second squared. So this one is correct. We're going to go back up to Grace's, and Grace has 2. But my question is this. Notice that instead of velocity and time, I have distance and time squared. And because I have distance and time squared, and it was originally a curve, if you start with a quadratic equation, whatever number you have here, you have to double it. And here's why. Notice that in this equation, okay, we've plotted the same thing. We plotted position versus time squared. And if we ignore this guy right here in the middle, you'll see that position versus time squared is only 1/2 of the acceleration. So our slope of 2 is only half the acceleration. So if we multiply it times 2, then we get 4. And if you remember in Pratyush's answer, Pratyush put 4 because that is the acceleration. That's the actual slope of velocity versus time. So that's the difference between doing distance versus time squared and velocity versus time. The slope of velocity versus time gives you the acceleration, and distance versus time squared is like this equation. It only gives you 1/2 of the acceleration. That's something that they do to you every once in a while on the AP exam. All right, very nice job. So now if I want to find the acceleration, remember we just plotted it. And if we did distance versus time, we have to multiply our slope by 2. And if we did velocity versus time, then we just use that value. So there's always a million ways to do this. So excellent job. We also have some other examples here. So this one is Row Along and Paulina, and they're trying to determine if a collision is elastic, inelastic, or perfectly elastic. And we could go through and talk about what to do on this one in order to find all that stuff. We could do the graph and those type of things. So if I want to know if a collision is elastic, inelastic, or perfectly inelastic, and I want to make a graph, what do you think I would have to plot in order to see whether a collision is elastic, inelastic, or perfectly inelastic? So let's do this. What's the difference between elastic, inelastic, or perfectly inelastic? The biggest difference is something. So what is it? We do know that momentum is equal to mass times velocity. But the mass times velocity for these is going to be conserved. So there's something else we can do. This one's kind of tricky. What happens to energy if you have an elastic collision? Is energy conserved or is energy not conserved? So there's a good question. On your slide, type in conserved or not conserved. So is kinetic energy conserved or not? Yes, very good. So somebody has written, if it is elastic, our kinetic energies are conserved. So that's fantastic. We're going to put kinetic energy original down at the bottom and kinetic energy final over here. So let's try that. Kinetic energy original and kinetic energy final. So we'll put kinetic energy original down on the bottom. Good. Excellent. Now, if it's conserved, what should our graph look like if we start with a small kinetic energy and move to a big kinetic energy. So each time we are starting the car with a different speed. So this one's a lot more tricky, I think, than some of the others. If it's perfectly elastic, that line should be linear, and it is a perfectly because it's elastic, the two should equal each other. So we call that a direct relationship. It goes right through zero and perfect. So now if my number is 4 for initial, it's going to be 4 for final. If my collision was not elastic, let's say that it was perfectly inelastic, which means the two things collide, then my kinetic energy beginning would be bigger than my kinetic energy final. So now that slope would shift. So that's a little bit more complicated. The only reason I wanted to show you this is it is different than what we were doing before. Most of the time, what we'll do is we will go through and you will only have questions where, here, I got to go back. You'll have questions where you're going to be able to draw a graph and have a slope that has a value. But every rare once in a while, they're going to go through and they might give you something kind of like what we were looking at in this very next one, where they're going to have you have some sort of relationship that you're going to have to show. Okay, so that is the end. I guess it looks like it's time to go. So remember, we're going to keep that conversation going in Discord, but not tonight. Instead, Brianna will let us all know when she's going to do that, and we will be able to do that. We've got about a minute or two here. If anybody has any questions, I think the big takeaway from tonight was try to use that D square. So anytime you write an experimental procedure, use D square. Remember that stood for diagram, then set up quantities and apparatus, and those three things go together. And then we want repeated independent variable and what you're going to do to change it. And then finally, error reduction. And that error reduction is super important. I'm going to end this presentation, but I'm going to go ahead and I'll put a link to the presentation in so that you have all that fun stuff. And today is the 21st. Please come back next week, because next week we are going to go through QQT and paragraph length, and those are the two that are on the digital exam. So if you're taking the digital exam in June, or you're taking, if you're taking that in June, or you're taking it, you're doing the digital exam, then you'll definitely want to show up for that. That'll be super important. In the chat, you'll see the link for the takeaways. Remember, that is a Google Doc that will show you all the stuff that's there. And I really appreciate each and every single one of you coming out today. That was amazing. You guys are fantastic. Please, please, please keep coming back. If you're watching these, keep watching them, and hopefully they are super helpful. So thank you guys so much for coming again tonight. You guys are rock stars. Next week, we'll hit it hard again, and then we've got our big finale, and we'll do 4 hours of physics, and we'll play games the last hour of that. So we'll give you more information next week. All right, guys, thank you so much again. We will talk to you later. Thank you for Brianna for being here, and hopefully later on in the week we can do a little Discord. Will the paper exam only have no? The paper exam actually has 5 different free response questions. There's a QQT, qualitative, quantitative translation. There's a paragraph length response. There is a experimental design, and then 2 which we call short answers. So we will talk about those other types next week, and hopefully that'll be super helpful. Anybody else have any questions? All right, again, thank you so much for coming, and we will talk to everybody at our next event. See you then.